Course is হ্যাঁ কাট অফ নিচে থাকে না মানে কিন্তু হ্যাঁ সিলেবাস আলাদা এখন ডেটা সায়েন্স আর এআই একটাই আরেকটা প্রবলেমস আছে ডিবিএমএস থাকবে এমএল থাকবে এআই সার্চ টেকনিক্স থাকবে ডেটা স্ট্রাকচারস এন্ড
বিশাল টাকা না আমি কম পরে দোকান
না আরেকটা আছে
পরে
নরমাল ক্যালকুলেশন নেব
বলবো
Everyone, and welcome back from a very tasty and delightful lunch. I hope you all are enjoying, you have enjoyed the lunch and you are all enjoying a great time at the Second International Conference on Applied Algorithms 2025. It's an honor to welcome you all to our final session of the conference, which promises to be both intellectually stimulating and insightful. We have a fantastic lineup for you, starting with an invited talk by the esteemed Professor Gautam Dash on coping with expensive distance oracles in metric space proximity problems. Following the invited talk, we have a session dedicated to track C, that's the industrial applications, which highlights the vital role that advanced algorithms play in shaping the future of industry. This track is a testament to the pivotal role of applied algorithms in driving innovation and efficiency across industries. As we move towards Industry 5.0, the convergence of human intelligence and advanced technologies is shaping industrial landscapes, promoting sustainability and enhancing human-machine collaboration. The 4 papers we will hear today reflect this transformative journey. The presentation segment will be followed by the valedictory session, which we will reflect the key takeaways from this conference. This will be followed by the vote of thanks, and then we'll have an opportunity to relax and network over high tea. Now, before we begin, let me introduce the distinguished individual who will be leading our session. The invited talk will be chaired by Professor Saurabh Chakraborty. Saurabh Chakraborty is a professor in computer science at the Indian Statistical Institute, Kolkata, India. He finished his bachelor's in mathematics from Chennai Mathematical Institute in 2003 and then went on to do his master's in 2005 and PhD in 2008 in computer science from the University of Chicago under the guidance of Professor Laszlo Babai. After doing 1 year of postdoc at Technion, Israel, and 1 year of postdoc at CWI Amsterdam, he joined Chennai Mathematical Institute in 2010. He joined the Indian Statistical Institute in 2018. His main area of interest is theoretical computer science, with a particular focus on query complexity, property testing, Fourier analysis of Boolean functions, streaming algorithms, and graph algorithms. Recently, he has been using property testing techniques in other more applied areas. We are highly privileged to have him here today. Without further ado, I would invite Professor Chakraborty to introduce our keynote speaker and begin the session. So please.
Welcome everyone. So it's my privilege to welcome Professor Gautam Das. Just during lunch, I was told a very interesting information that Gautam Das is one of the 2 people who also presented in Icaa first one. So 10 years back. So clearly Gautam Das doesn't need much introduction in this community, but still I will do the honors. So Dr. Das is currently an Associate Dean for Research in College of Engineering, a distinguished University Chair Professor of Computer Science and Engineering, Director of the Center for Artificial Intelligence and Big Data, and Director of the Database Exploration Laboratory at University of Texas, Arlington. Prior to joining the University of Texas, Arlington in 2004, he has held various positions at Microsoft Research, Compaq Corporation, and the University of Memphis. He graduated with BTech in Computer Science from IIT Kanpur in 1983 and with a PhD in Computer Science from University of Washington, Madison in 1990. He is a fellow of IEEE and a fellow of ACM. His early research interests were in computational geometry and graph theory. His PhD dissertation made several significant contributions to important problems in this area, including the discovery of greedy graph spanners, the discovery of exclusion regions for minimum weight triangulations, and determining the complexity of convex polyhedral separability. In the subsequent decades, his research interest broadened to all aspects of big data exploration, including data management, data analytics, machine learning, and data mining. Some highlights of his contribution has been on keyword search and ranking in database, time series mining, approximate query processing, and deep web analytics. He is presently working in areas such as machine learning approaches for approximate query processing and fairness and explainability in data management systems. Dr. Das has published quite a number of papers. Here it is written 200 papers. I'm sure it's much more than that. Many of which have appeared in premier data mining and database and algorithms conferences and journals. His work has received several awards, including Communication of the ACM Research Highlight in 2021, ACM Sigmod Research Highlight in 2019, IEEE ICT 10-year Influential Paper Award in 2012, ACM KDD Doctoral Dissertation Award in 2014 for his former student and numerous other awards. He has presented keynote and invited lecture, tutorials, and courses at various institutes, research labs, and conferences. He has been on the editorial board of Journal of ACM Transactions of Database Systems and IEEE Transactions on Knowledge and Data Engineering. He has served in organizational roles of several major conferences, including as General Chair of ACM's Sigmod and PODS 2018. His research has been supported by various grants from the National Science Foundation of US, Army Research Office, Office of Naval Research, Department of Education, Texas Higher Education Coordinating Board, Qatar Foundation, AT&T, Microsoft, Nokia Research, Cadence Design and Systems, and Apollo Data Technology. I'm sure I can keep on going and say more about Dr. Das, but I think it's better that Dr. Das takes the stage and not this whole.
Thank you very much for the kind introduction. And had I known that you're going to be introducing me everything this way, I would have given you a much more shorter list. So sorry about that. It's a great pleasure and honor to be here. I was a guest, as we mentioned, back in 2014. So it almost feels like coming back to home. I see a lot of familiar faces, and of course, a lot of new faces, a lot of new constructions. So I'm really happy to be here. It's an honor for sure. So I wasn't very sure what kind of a talk to give here. The topic of the conference is applied algorithms. So I selected some work which would be a little bit aligned with the topic of the conference. So I'll be talking quite a bit about algorithms, in particular about graph algorithms. And at a very basic level, the kind of graph algorithms I'll be mentioning here in this talk is going to be anything that even a undergraduate student in an algorithm course knows about basics, how to spot, and so forth. The interesting thing about this work is, even though some of the fundamental research in this area has been 3 decades old, 4 decades old, we are looking at it from a new lens. We are trying to see how we can apply it in modern database systems and modern information systems. So that's, I would say, would be the novelty of this work. Okay. Let me know if you're hearing me well or whether I need to put on a different mic, because I sometimes walk here and there. I think I'm okay. All right. So the topic is going to be to address the problem of what are called expensive distance oracles in metric space proximity problems. So I'll define all of these terms in a minute. And once I define these terms, we will get into what is the application domain, why these things are important. So just wanted to mention that this talk is a summary of 2 pieces of work we have been looking at very recently. One is a paper that appeared in ACM SecMod conference in 2021. And these are my co-authors. Most of them are my students. So Jeez is a student, and he is a former student. He is at Microsoft now. Suraj is a former student. He just joined IIT Bombay. And Sajiti Basu Roy, she is a student who graduated about 13 years ago, and she's a full professor at New Jersey Institute. I was very proud of all these people. So this is work I'm still doing with a lot of my students. And we also got some very recent unpublished work, and I'm taking the liberty to talk about it today. So what is a metric space? Most people probably know what a metric space is, but this is how we define it. So you imagine a set of objects O, and there are n objects, and imagine that there is a distance function. So there's a distance function called d, which takes in a pair of objects and it comes up with a number. Okay, so that's a number between 0 and infinity, and typically these are positive distances, and that's what a metric space is. But there's a little bit more to it. What is more to it is that we've got effectively this thing called the triangle inequality. So if I take any 3 objects and you look at the distance between object A to object B, object B to object C, then you know that the distance from object A to C has to be less than or equal to the sum of the 2. So that's the triangle inequality. And when that applies to this distance function, that's known as a metric space. Okay, and metric spaces abound in a lot of applications. This is nothing new. Most distance functions are metric distances. So, for example, applications are sort of spots. If you look at map databases, if you look at mapping algorithms, they work off things like sort of spots and route networks. All of these obey metric space properties. You also look at image comparison. Let's say you want to define distances between images like house-top distances. They also obey metric space properties. Vector distances also obey metric space properties. Medical applications like CAT scans and fMRI comparisons, again, metric spaces. Protein database search, DNA sequence analysis, again, examples of. There are only very few examples of distance functions which don't obey the triangle inequality. It doesn't make a lot of sense for sort of the direct distance between 2 objects to be longer than an indirect distance. That's the reason why metric spaces are very important. Okay, so I hope I've convinced you that there are a lot of applications for metric spaces. And then, for time immemorial, people have been looking at what I loosely call proximity algorithms. So proximity algorithms are algorithms that work over data sets that obey distance functions which have metric space properties, and try to look for substructures inside them. So examples of very classical proximity algorithms are like the minimum spanning tree, right? So if I give you a bunch of objects and I tell you to find the minimum spanning tree, it'll try to find a substructure of the complete graph and try to find out the substructure which is the lowest weight, and this all based on distance function calculations. Sorted spot, another very classical problem, everybody knows about it. K nearest neighbor is one of those early machine learning algorithms before it was known as machine learning for trying to find out how to classify certain objects, and K-meter clustering. Clustering is another example of algorithm that uses distance functions in this calculation. So all of these are very classical algorithms, which is what I loosely call proximity algorithms, because they're all based on nearness properties or distance properties. Okay. So the thing that we look at on new lens is the architecture of execution. So if you look at traditional algorithms researchers, they really don't look at how the distance functions are exactly executed. But in real world, this is how it happens. So you got a what I call an oracle, like a central server somewhere, and you got like an edge device, like a laptop or something like that. And what happens is the edge device, which is running the proximity algorithm, it has to make oracle calls to the central server to ask it questions like, okay, tell me the distance between object A and object B. The edge device doesn't have that capability. And sometimes the metric space distance functions can have high monetary costs. As a very simple example, if I want to find the distance between two complicated images, I may want to use a library function, right, to do that. And that may have a large either monetary cost because somebody has to buy their software, or it may have a large time cost because the library has to execute, right? So the distance function could be either computationally expensive or it could be monetarily expensive. Another example would be if you want to make calls to the Google API to try and figure out what's the distance between two cities, right? Or between two points of interest. So you're making a call to an API and it's going to slow it down. And sometimes it can become difficult to make that API call because you're in a place where the internet is intermittent. So your edge device doesn't have the capability to make distance calls willy-nilly at any time they want to. There are all these budget constraints that so this is what is the new twist to this problem. That under this architecture where the oracle is an expensive oracle, how do we revisit some of these proximity problems and design algorithms which are sensitive to this particular cost? Okay. So our goal is to speed up proximity algorithms in metric spaces by applying certain techniques that will try to minimize these costs. So, this is what a typical proximity problem looks like. If you take a snapshot of this proximity problem, it really looks like this. So you've got objects, you've got distances between objects, and whenever you make a distance call, you make that expensive oracle call, the distance between two objects is known. But then there are many other objects you may not know the distances between those. So as and when the oracles get called, this graph is getting slowly dense, it's getting filled, right? And you always have the triangle inequality to worry about. You cannot, go against that paradigm because that is what is a part of the definitions of the problem. So this is another example. So you can see that some proximity algorithm, we don't know what it is. Is it the shortest path algorithm or the spanning tree algorithm or K-meter or whatever. As an algorithm progresses over the input data, it's starting to make this graph more dense. So the known part of the graph is becoming more and more dense because certain edges are getting resolved by making all this calls to the oracle, but there are many edges which are still not known, right? So depending on how the proximity algorithm makes this call, the graph will get more and more, it will reveal its nature and the structure as the algorithm progresses. So this is another example. The blue lines represent all the oracle calls that have already been made, and the yellow lines represent the upcoming oracle calls that the algorithm is going to make. And our objective is to try and get in the middle and create some sort of simpler processes by which we try to minimize these yellow calls. So we have already made the blue calls, we can't do anything about it, but try to redirect the oracle to try and minimize this yellow calls. It will become a little clearer as I start getting into some more details, but this is the essential idea. So we're looking at trying to reduce the complexity of this proximity algorithms with a new notion of what is the complexity. Okay. So most of these proximity algorithms have this ubiquitous if statement. So it's really like this. When you look at spanning trees, shortest paths, any of these algorithms, at the heart of the algorithm, they're comparing distances. there is some code somewhere which says, is the distance between object OI to OG bigger than the distance between object OP to OL? If it is, you do something, or it's do something else. So that's really how these articles work, these algorithms work. So what we want to do is want to look at that statement more carefully and try to see whether we can rewrite it in a different way, which will allow us to reduce these costs. So if we can put a lightweight, a very low cost extra function called what I call a check function. So if there's a lightweight check function which can tell you ahead of time in advance whether a particular object pair, its distance is going to be less than the other side, then you don't have to make the actual oracle calls to reveal the exact distance, because the exact distance costs can be expensive, right? So this is really what we want to do. And if your check function doesn't work, if it doesn't able to do the job, then you actually go ahead and do the actual oracle calls. So that is where we try to save. So what would be an example of a check function? The idea is to transform a problem into a feasibility test as a linear program. So I'll tell you a little bit more about what I mean by all the statements. So let's take, let's try to model the problem as follows. So I'm at my edge device. I've got a laptop or whatever, and I have already got a part of the graph revealed to me by all the oracle calls that have been made. And now there is a new pair of nodes on which the proximity algorithm is trying to figure out what the distance is, right? So, and then maybe it's comparing it with another edge on which the distance is not known. So what I want to do is, I want to look at the graph that I have with me. At the client side, I have the graph, and without making a call to the oracle, I want to figure out from the client graph whether I can provide some kind of a bound as to what the distance could be. So we model it as a linear program. So we create for every unresolved distance, we create a variable. So if there's an unresolved distance, which is OI, OJ, we create a variable called Xij. And then we know that every triangle inequality, so if there are n nodes in this graph, there are n cubed different triplets. So you can create n cubed different triangle inequalities of this kind. All right, and then if you look at the if statement that this algorithm, the proximity algorithm is asking, if there is a state statement that's comparing a couple of distances, what I do is I just put that as a condition, as an extra condition, and then I ask this linear program, is this feasible? Do you have a feasible solution for this? If there is a feasible solution for this, that basically gives you an answer to the if statement. And if you don't have a feasible solution, then it says that the if statement has to follow the else part. So this is important, that to answer the if statement, you did not have to go to the server. You didn't have to go to the expensive server. You worked only locally with your client graph, and we are able to come up with a direct feasibility test. Now, the problem is, yes, you didn't go to the server, so you didn't have to make an API call to Google or wherever you're getting all this exact distance, but you have to solve a really, really large linear program. And that itself is locally also expensive. So that is the problem with this direct feasibility test, that even though it can produce really good tight bounds, but the problem is you're solving this really large linear programs having quadratic number of variables and cubic number of constraints. And what you gain by not accessing the large expensive server, you lose by making local processing to be unscalable, right? I mean, nobody who works in data science will agree to anything that runs in n squared time or has an n cubed space or anything like that, right? So these are all impractical solutions, but they provide a basis for us to kind of try to do things better. So the next idea that we had was let's revisit the check function and see whether we can do something even simpler than trying to do this linear program. So we found that if you have a original if statement which is comparing two distances, instead of making this oracle calls, if somehow we can have a quick way of finding the lower bound, some kind of a lower bound for one of the distances and some kind of an upper bound for the other distance, then you know that if the lower bound of the thing on the left hand side is bigger than the upper bound on the thing on the right hand side, a little up, okay. Is it better? Okay. So So if you're asking, if the algorithm is trying to ask, is DOI/OJ bigger than DOK/OL? We can put a lightweight check which says that if the lower bound, somehow magically, let's say we manage to get the lower bound. If the lower bound of OI to OJ is bigger than upper bound to OK to OL, then we're done, right? Then you can follow the F path. If that is not true, then we actually have to make those expensive oracle calls. Then we go ahead and do these proximity oracle calls, and then you follow the rest of the code. So this is an easy way to try and avoid as many oracle calls as possible. So the question is, how do we, create these algorithms for creating upper bounds and lower bounds, which can be done very quickly. So what we did in that Segmont paper is really basically that try to create this lightweight, very, very efficient upper bound and lower bound oracles of missing distances in a graph which follows metric space properties. So we want to answer questions like lower bound queries and upper bound queries between pairs of nodes in this graph. Okay. Just stop me anytime you have any questions. I don't want to lose the audience. I'll try to keep it as basic as possible. But this is the first time I'm actually giving this talk, so I'm not sure how this is going. So the upper bound oracle is actually a well-solved problem. So here is the idea that suppose this is a piece of the graph and you're trying to find the distance between Vi to Vj. So those top two nodes, right? And you don't know what they are. You could, of course, go and call the oracle and get that answer. That's expensive. However, we know that we can apply the triangle inequality out here, right? So you know that the distance between Vi to Vw is less than or equal to the sum of those two distances, right? Vi to Vu and Vu to Vw, right? We know that. And if you extend this a little bit more, you know that the distance between Vi to Vx is less than or equal to that path length from Vi to Vx along that particular path. And likewise, if you keep going, the distance from Vi to Vl has to be less than or equal to the length of that path from Vi to Vl in the part of the graph that you've seen. So what it means is that if you don't have any further information, you only have that part of the graph that you've seen so far. The upper bound oracle between any pair of nodes is simply the length of the shortest path between those nodes. And shortest path problem has been studied forever, and there's nothing new for us to do here, right? You've got approximate shortest path oracles, you've got the classical that's the shortest path and all that. So the upper bound oracle is not a new research problem, so we did not focus on the upper bound. However, the low bound oracle is a very interesting, very different problem. Very little studies have been done in it, and I'm going to talk about that. So the low bound oracle is the smallest distance that a particular pair of nodes can take without violating the triangle inequality, right? So we looked at past work as to what has been done in this space, and the only thing we could find was, well, actually we found a couple of papers. One was this Dennis Sasa and Wang. They wrote this paper back in 1990, which is a one-shot algorithm to find out lower bounds between every pair of nodes on which the edges are not yet resolved. So they try to give a lower bound on what it could be. So it's based on a dynamic programming approach, but it is very slow. It is not a scalable algorithm. It consumes in-cube time to solve this problem. So it's not something that can be used in modern databases or data science applications. And every time the graph changes, you need to have so for example, if the proximity algorithm creates another edge in this graph, you have to take quadratic amount of time to update your data structure. So this is not going to work. But it produced a lot of interesting ideas for us, which we could capitalize on. So here is one of the ideas that we applied. And again, remember, we're trying to find lower bounds. That means we're going to try to say that between these two nodes, the distance cannot be smaller than a certain number. If it is smaller than a certain number, it will violate the triangle inequality. So again, going back to this picture, let's say I want to find out the lower bound between Vi and Vj. Let's assume that we have a path in the known part of the graph, right? In the known part of the graph, there is some path. Now let's take an edge in that path. Let's say Vx to Vy. And you'll find out later that taking the longest edge is a good idea, but let's say that there is an edge there. So here is what you can see, that you can immediately create a lower bound on the distance between VW and VY. Because of the triangle inequality, you know that VW to VY has to be greater than equal to Vx to Vy minus Vw to Vx, right? I mean, you cannot have a very small number for Vw to Vy because that will violate the triangle inequality. Right? So if you carry this idea out, the distance between Vw and Vc is again can be written in this sort of form where you're adding and subtracting distances, right? So these are all ways in which you can fold the path to create a lower bound. And eventually, as you wrap the path onto the edge that you're looking at, this is what happens. So you've got these two nodes on which you're trying to find a lower bound, and you pick some arbitrary edge on which there is a path. Then basically, the lower bound is the length of this edge minus the length of those two paths. So that's how you fold it, all right? And that's it. That's the simplest idea by which you can get at least a lower bound. So you have got these two nodes, you find any path, take any edge on that path, better to take the longest edge. The lower bound on that missing edge is the longest edge minus the sum of these two edges, the sum of these two path lengths. Any questions so far?
Yeah, so that subtraction, since I it is in the low part of the graph, I can always make it positive, right? Because you are just subtracting from two edges.
Mhm.
One of them is negative, one of them is positive. Right?
Yeah, so basically, okay, so this picture will make it clear. The lower bound from Vi to Vj has to be greater than or equal to the length of Vx to Vy minus the length of the path from Vi to Vx minus the length of the path from Vj to Vy. That's really what this folding thing says.
The triangle you are writing that this is must be greater than or equal to this minus this. I can as well write this minus this. So when you are writing, it would be like dw ox minus dx. I mean xy, right? Because within the triangle, the other two edges doesn't have a direction, right? I mean, they just can be this minus this or this minus.
Well, I mean, yeah, of course.
And one of them is negative, other one is
Yeah. So, yeah, of course. I mean, you see, ultimately, to get the low bound, you take the largest number you get. Yeah, exactly.
In the lower part of the graph, it doesn't matter.
It doesn't matter. Exactly. Yes.
Why do you say that the distance between Vx and Vy should be as large as possible?
Oh, why do I take the longest? It doesn't matter. Ultimately, it will work for anything. If you take the longest edge, then you'll get a large lower bound, right? You'll get a large lower bound. So that's the basic idea. Okay. So I think everybody got this edge folding idea. The question now is how to do it fast, right? So I have this graph.
I have one last question.
Yes.
Vx, Vy is a single edge.
VSB has any edge on that graph.
The longest edge in that path or whatever.
Longest is a good way to improve it, but it could be potentially any edge.
Yeah. But with that OWOX, Y to prove that.
Mhm.
Okay, they are also just two edges, right? Yes, fine.
It's good. Alright, so this is the algorithmic problem that we have to solve, which is like, let's say I have a graph. It's a subgraph of the complete graph. It's the same part of the graph. Now I take two nodes which don't have a direct edge between them. I'm asking the question, what kind of a number can I put on that edge weight so that it doesn't violate triangle inequalities? Can I put a lower bound on that? So what I'm saying is that there is, in principle, algorithm. We just need to make it fast. Algorithm is take any path from that node. Okay, take any edge on that path. The lower bound has to be this edge minus these two path lengths added. So you just do it for every path, and you get the best number. That's your number. That's the algorithm. Okay. Of course.
So what was the told? You are getting different algorithm for that. What he told us that you can ensure every edge you are bound positive. Effective what you are getting positive quantity. That's what he told. And it's about the A minus part,
Mhm.
it might be.
But then you put a max of 0, right? I mean, 0 comma, sorry?
No, max of 0 is fine, but you will get a positive actually, bigger than 0. But when you are looking at the A,
That's not really true, right? I mean, suppose I have a triangle which is, okay, so let's say that there are 2 nodes. I don't know the edge between those 2 nodes. Then I've just got I've got one edge to another node, one edge to another node, one edge to another. All these 3 nodes have edges 1. Okay,
So he is finding n minus one lower bound and takes the max lower bound. Is that the idea?
that's the idea.
That's the worst case.
Yeah, that's the one. No, but not n minus 1, the number of edge for
The number of
each.
edges on the path will be n minus one. They are n bodies around.
Right. But then there are also many paths, right?
I was a K. N is the total number of bodies on the graph.
Okay. Yeah, this is getting interesting. So, what I've given you right now is a sort of a deterministic algorithm. What I haven't given you is an efficient algorithm, right? No, that's fine. That's fine. I mean, as I said, this stuff today is all about what we do in undergraduate algorithm courses. There's nothing fancy about it, but it's an interesting new look at some of these problems. Okay. Clear? All right. So really the objective now is how do I do this edge folding fast, right? I mean, in data science and all databases, you cannot have n squared, n cubed, you cannot have linear. Everything has to be constant time or sublinear, logarithmic. That's the kind of approach you need to have. So this is really the challenge that we are facing, right? So since I'm done with this, let me move on. Okay, so we did a little bit of algorithmic work here, and what we found is that we can do a one-shot algorithm. So for a single edge, we cannot do anything fancy. For a single edge, we really have to run Dijkstra sort of spots. So we are getting into linear, a little bit more than linear territory. But what we could do is we could, in a one shot, find out lower bounds of all the remaining missing edges. And we could do fast. So that was one improvement we did so far in this particular work, this remote work. So what happens is that, okay, let me just quickly go over it. Yeah, so basically one thing we observed is that for a good bound, the dotted paths from Vx to Vi and Vy to Vj must be general shortest paths. They cannot be long paths. If they're long paths, then they're going to give a bad lower bound, right? So we need to have shortest paths. So really it boils down to calculating shortest path algorithms as quickly as possible on the fly. And when the proximity algorithm is trying to do this if statement, somehow we need to get into the game right there. And before it starts executing those expensive server calls, we need to start doing our shortest path algorithms on the known part of the graph and come up with a lower bound. And if the lower bound helps the check function, we avoid making the expensive distance calls. So that's the objective. So basically, we reduce the problem to a single call for Dijkstra for every edge on which you want to get a lower bound. So it is clearly better than solving that linear program. The linear program was, a linear program with n cubed constraints and n squared variables is not a simple job. I mean, this is a lot faster, but of course, it's not as good as the linear program because we're having kind of a looser way of trying to find it. So, so if you just take a step back and ask, what have we achieved so far? Well, what we've achieved so far is that, take that old Dennis Salsa paper of 1990, that was a single shot algorithm. So that was not a query driven algorithm. It doesn't resolve the low bound for a given input unknown pair. It finds out the low bounds for all the unknown pairs, and it ran in this very slow n-cubed algorithm. And we're doing no better. We are also running an n-cubed log n time because we're running Dijkstra n squared times, right? Because there could be n squared missing edges. So in some sense, we have not really gained. What we have gained is on a per query basis, we have got it to, almost linear. But, when you have to solve all the missing edges, it's again back to n cube. So, so one of the techniques we started looking at next is what we call path expansion. So let me see what this is. By the way, these slides were prepared by my students, so a little bit of it is I'm also unfamiliar with some of them. So the idea in path expansion is that, if you look at this whole idea of low bound computations, it's for every missing edge, it looks at the path and it does this edge folding to find out the lower bound. The point is that these paths are common across many such pairs. So we're going to take advantage of the commonality of these computations to cut down these calculations. So the point is that the path that corresponds to the low bound is optimal for many more paths. And a very simple example will make that clear. So for example, if this was the path, that specific path which gave you the best lower bound between those two green nodes, you can see that that particular path is also good for that other pair, that green node VI and the other node which is one below VG, because the shortest spots are still the shortest spots, right? So we take advantage of this commonality in some pretty, again, basic architectures, basic algorithms, but we take advantage of this to cut down the running time.
Total information that you need to store locally is still linear.
Total information we need to store locally here in this particular, you mean to solve the single shot for everything?
Whatever you do, if you are avoiding the API call, you have to do something local, right?
Yeah, local for sure. When whatever graph is being created, we are creating a copy of that. That is given. So any other data structure we put on top of it, we try to stay within that. Help answer your question?
So if you have quadratic edges, do you have to store a lower bound for every edge, or there is a sort of, greater than less than dominance relationship among the edges?
So this particular algorithm that I'm describing, this one right now, I'm trying to find out for all the edges. But we also have if you remember, I told earlier that we also have a query-based thing, right? So we have a graph which is known to us that has m edges. Hopefully m is a small number, it's not n squared or whatever. There are m edges, and there could be a query that for node vi to vj, what's a low bound? For that, we just reduce it to running Dijkstra, that's all. Now, for finding out for all the different edges, that's why we're trying to do something a little better.
Right, the target application. It's like every mobile will store a part of the graph, that sort of an application.
Yeah.
But if you are liking to use it for low memory robots or something,
Mhm.
your application, we do have memory for quadratic space.
Well, I mean, so here's the thing, and a lot of these proximity algorithms, they really never get close to looking at quadratic time and quadratic space. So, for example, if you run the minimum spanning tree algorithm, right, the size of the tree is linear, and the running time is pretty much linear, right, n log n or whatever, much smaller than quadratic, right? So, in fact, the path of the number of pairs it checks by simple definition has to be less than quadratic, right? So that's really what is going to be stored at the local server. I mean, at the local edge device. Okay. All right. So how are we doing in time? I have a few half an hour now, with plenty of time. Okay. All right. Okay, so this because of the commonality, we can take advantage of the commonality because these low bound paths are shared across multiple pairs, so we can take advantage of that. So I'll not get into the details, but this is what we did. We maintained a data structure that maintains potential paths, which can yield tighter low bounds for pairs of nodes, and blah blah blah. I don't think it's important for us to get into these details, but somehow we do some intelligent stuff to take care of this commonality. But the high-level summary is that we could use a very elementary data structure, Fibonacci heaps. I'm sure everybody who's done an undergraduate course in algorithms has seen that. And the interesting thing is that the overall running time of our algorithm is n time n plus n squared log n. So it is, if m is small, it's a pretty small number. So it is not running into, n cubed and all that. Right? So if m is small, it is not a big number. Okay, then the question is still all of these, linear time and all of that is still not acceptable. We really want to go down to constant time per query. We really want to go down to maybe logarithmic or sublinear. That's really what practical applications demand. So the question is, could we do even better than some of these classical algorithms approaches, graph algorithms approaches? So then the question is, what about approximate low bounds, approximate upper bounds. Why do we insist on the upper bounds being exact sorted spots and lower bounds being all the edge folding stuff, right? Do we have to really do all of that? We just want a lower bound, right? We want to just help our check function get in the way of the proximity algorithm and do something quick, right? So what about approximate methods? So again, for upper bounds, there is not much of research that we need to do. So if you know the history behind graph algorithms, sorted spots was of course the first sort of problem, but then we have also had after that approximate distance oracles, right? There's the entire area of approximate distance oracles which tells you how to find approximate sorted spots in a graph. And so we can just take those off-the-shelf methods and apply it here. And that's why we didn't focus on the upper bound problem. But then this lower bound problem is still a very unique, different kind of a problem. So we started to look at how we can do things in an approximate way for lower bounds. Okay. So one of the simplest ideas which we tried first is what we call a k-parameter search. So everything in lower bounds are driven by paths, right? Alternate paths. So if I want to find the lower bound between any pair of nodes, I find a path and I do the edge folding, I get a lower bound. I find another path, I do edge folding, I get another lower bound. If I exhaust all of this, I get my best lower bound, right? So why do all that work? Why not just find a few paths and get a lower bound, which is may not be the tightest, but it's an approximate lower bound, right? By the way, I'm using the word approximate with a with a qualification. It's not an approximate lower bound in the classical theoretical algorithms community, that we don't really prove an approximation factor or anything like that. It is a heuristic approximation, and that's what we have. So here the idea was to explore paths of length k. So don't go for long paths, just go for paths of length k and speed up the algorithm and try to understand. So one simple idea was, which actually worked very well in practice, was we called tri-scheme. That's simply paths of length 2. So if I have an edge, I don't know the lower bound for that. Look at all the triangles that edge participates. That's all. Look at all the triangles and just find a lower bound from all those triangles and use that as a lower bound. It will be, of course, a loose lower bound, but this stuff is blazing fast, right? I mean, the running time of this query is basically equal to the degree, right? The sum of the 2 degrees. So we are now getting it close to, constant time, right? Because the average degree of a node in a graph is m over n. So our running time of these algorithms, it's a very simple algorithm, but it actually works very well. And of course, it's very, very fast. So that was the idea, tri-scheme. And then we discovered another set of papers. So these are called node landmark papers. So here the idea was that they again based on metric space proximity problems. So this particular paper, what it did is, if you have a set of objects, instead of finding out all pairs distances and making all these complex calls, they pick a bunch of k nodes. They call them landmarks. So k is typically a small number. So then what they do is they find the distances from every other node to each of the k nodes. So the total number of expensive distance calls they do is k times n, not n squared, right? So k times n is hopefully a small number. The landmarks are small and judiciously selected. It's like this, if I want to, it's again connected with, routing through hubs and all that, right? So if I want to send a packet from point A to point B, ideally I'd like to send it on the direct edge, but if I send it from point A to some kind of a central post office, that central post office sends it to the regional post office, then it makes its way to point B, it increases the number of hops, but then the total number of edges that have to be pre-processed in advance is minimal. So this was the idea of node landmarks. So all they did is they picked a few landmarks and they use heuristics to figure out which are the landmarks they should pick, connected with what is called the facility location problem. And then they pre-computed these edges. So they made all this, to prime their algorithm, they made all these expensive oracle calls, but at most k times n of them.
Landmarks are chosen by the algorithm. They are not pre-chosen landmarks.
No, so when we say algorithm, we have to be careful, right? So there is a proximity algorithm which we don't know what it is doing, right? It's a meta algorithm. It could be, we have no idea which particular pair of nodes is going to ask. We are trying to create a sort of the client side, at the edge side, we're trying to create a data structure which will help us answer those, try to avoid those proximity, query calls. So this is the landmarks are done at the client side. They basically, before anything starts, before the world starts, they pick Keynotes. They solve what is roughly this facility location problem. But of course, this is chicken and egg problem because facility location problem requires you to know all the distances. They don't even know that, right?
There is something called island search in heuristic search in AI that is
Probably.
Islands are being computed. So we should ask where they get.
Probably, yes. So this is, so they use heuristics to figure it out. And, once they fix the landmarks, everything is driven by those landmarks. So if I want to find the lower bound on a particular pair of nodes, I simply find out from node A to any one of the landmarks back to this node, I get a lower bound. Node B to another landmark, back to this node, I get another lower bound, I get the best of all the lower bounds. This is a very simple algorithm. The problem with this approach is that it assumes that the client has got access to the expensive server. So there are two guys which have got access to the expensive server. One is the meta algorithm, which is running the proximity algorithm. And you're also having this client, which also is making all these calls, right? In certain situations, the client may not even have access to the server at all. So it cannot even create this pre-processed data structure which will allow you to do this. And that's where we sort of started looking at different ways of doing it, where all we have is this graph. We don't make a single call to the expensive server. So that's why the thing I'm going to talk about next is a little bit different from what the node landmarks did. Okay. So just to summarize the try scheme, a very simple algorithm. As I mentioned, that it actually has an average query complexity, average in a loose sense. This is not a randomized algorithm that it has expected complexity or anything like that. But if you run it over all the missing edges, the amortized running time would be m over n, which for a small m, for a not a dense graph, is pretty much almost constant time. Already a big improvement. But then the low bounds were not very good because it simply assumed that I'm just going to look at paths of length 2. I mean, there could be longer paths which you're not able to exploit. Right? So this is all sigmoid work. The last year we have been looking at sort of taking this idea of node landmarks and trying to create something similar called edge landmarks. And where we still have the advantages of node landmarks, the simplicity of node landmarks, but we don't have to make all those priming calls to the oracle. We just go with the graph, whatever graph we have with us. So this is work under submission. We're crossing our fingers and hoping that it gets accepted. But I'll talk about it nevertheless. So the idea is that we want to design a technique which will not make a single call to that expensive distance function. We're just going to take it as a purely graph theory problem. There's a graph with us. There are missing edges. We want to find a low bound for the missing edge. And the technical way of doing it is the edge folding idea. We just want to do it fast. We want to allow approximations and so on. And we want to ideally do it in order 1 query time. So we don't want to spend a lot of time doing this, right? So our solution was really to select, so we've got this graph, blue edges. Somehow judiciously select k edges of this graph. K is a small parameter, hopefully. Now these are going to be called edge landmarks. So once we have k edges, then all our low bound calculations are going to be driven along these k edges. Remember that every edge is used for a folding operation, right? You take that edge and you take the shortest paths to the 2 nodes and then fold it, right? So instead of folding it over every edge, we're going to just fold it over this k selected, pre-selected edges. So that's the whole idea of edge landmarks. So what we need to store, okay, I don't know what is all this here. Yeah, so it's just this is a recapping the previous structure. So basically what we need is for each of these edges in the landmark, we need to know shortest paths from every endpoint to every other. So all we need to do to prime up our algorithm is to run Dijkstra from every of the 2k endpoints. There are k edges which are picked as landmarks. So you make a Dijkstra call to, you make 2k Dijkstra calls, and that's it. And once you're done with that, query answering is basically order k time, because when you have a missing edge, you just look at each of the k landmarks and find out what are the distances to each of the vertices of the missing edge. So the query time takes order k, and the total space consumed is linear, k times n. And so that's really what we do with this. So this is, in a sense, our sort of final result, in the sense that it doesn't take any time at all to answer queries. It only takes linear time and space to set up the data structures. It doesn't make any function calls to the expensive Oracle, unlike the node landmark paper. However, there has to be a catch, right? This is all too good to be true. The catch is, these are all approximate results, and we don't have any proofs as to how good the approximations are. We only have some experiments to show that, okay, they did well in practice and all, but we don't really have any proof, theoretical proof of anything. So those are all open problems. Yeah.
Because for each edge, you consider every vertex, the source and every vertex.
So yeah, so if you think of each, there are k edges, right? So each edge has two endpoints. So there are two k special nodes, right? And from each of these two k special nodes, you find the shortest paths to every other node, right? Okay. And you need to store it. So you need a table so that you can do quick lookup. So that's why you need order k in space also. So this is a little bit more than linear. I mean, but again, in real world applications, if k is 10, you're blowing up your memory by 10 times, right? So there are all issues to worry about. So, but yeah, that's right.
Even if I make a map query, I'm not going to make it the whole world. Maybe I'm going to make it the sea or.
There's a lot of opportunity to take these basics ideas and sort of make it even more practical. So the interesting thing, what we did, other interesting thing we did here is how do we select those k edges? So if you look at the node landmark paper, they're all connected with this facility location problem approach, except that it's a chicken and egg problem because the data, the distances are hidden behind this wall. And even if you have the graph in front of you, you can apply all those facility location algorithms and come up with, or clustering algorithms or whatever, right? But if the data, the distances are hidden behind this expensive function, it's a chicken and egg problem. So in our case, that is not the case, right? We have the graph. The graph is at our client side. We just need to pick k edges so that the lower bounds that we get through those k edges is as good as possible for all the remaining edges. So we actually have a very well-defined optimization problem that we want to solve. Unlike the node landmark paper, because that's like a chicken and egg problem. It just can't be solved in a principled manner. So the optimization problem is how to select those k edges. We basically have to pick those k edges as that, let's say some aggregate. We use the sum aggregate, the sum of the lower bounds we can get for all the missing edges using this k landmark edges is maximized, right? So this is the objective function. And selecting k edges which maximizes the objective function is not a easy problem, it's a hard problem. In fact, it's an NP-complete problem. So unless we have some real, breakthroughs by somebody from your community, this is not going to stay easy. But what we found is that this particular problem it can be tackled by some very simple classical methods. So, for example, we found that it has two properties. One is monotonicity. In other words, if I picked k-1 edges as my landmarks and frozen them, I add one more edge as my kth landmark, this optimization function is going to improve. So that's the monotonicity problem. The submodularity problem is basically that if, well, I don't know how easy it is to describe it here. If I have a set of, let's say, I don't know, k-2 edges at my landmark, then I have a particular edge, like let's call that edge E. If I add k-e to the set k-2 to create a new landmark set of k-1, whatever I get from my optimization function gain, if I took a superset over the k-2 and I added that edge, I will get an even better. So that's really the submodularity. So these two properties help us use a very simple greedy algorithm for this problem. So, simple iterative greedy algorithm is, and again, this is all textbook stuff, nothing fancy here, so that you can actually get a good approximation for the best k edge landmarks with an approximation factor of 1 minus 1 over e. So this has a running time of k n squared m, not particularly good, but it is still better than some of those previous things. The final statement I'll make is that we can actually do even better by using sampling to speed up our greedy algorithm rather than just making it run in a deterministic manner. So the idea would be to when you're trying to estimate that optimization function, that lower bound, max of the lower bound, you can instead of calculate the exact optimization function, you can actually use sampling method, just uniform random sampling to be able to estimate this. So that would make it even faster. It introduces some errors in certain steps, but that I would say would be the most practical algorithm which operates on some sort of principles. So the final pre-processing time is exactly what is shown here. S is the sampling fraction, which typically is a constant. K is a small landmark number, which is typically a constant, times M. M is the graph size plus N log N. So that's the only pre-processing. We're going to reduce all the pre-processing to really equivalent to a single run of Dijkstra, right? And then the query time, as I mentioned, is order Ks. So that's why all of this is really impressive in terms of running times. But what matters now is how well does this do in practice, right? When you see it running on real data sets, what kind of results do we get? Because we don't have proper guarantees on approximation and all that. All right, so very quickly run through experimental results. So we took a few data sets. There was a San Francisco point of interest data set, a Flickr 1 million image data set. We also took this urban GP data sets, which is again a map data set which describes places in Great Britain where they've had traffic accidents. And these are some of these parameters of the data sets, the number of nodes, the number of edges, and so on and so forth. Okay. And the distance function we typically use for the first and the third map data set was the Google Map API. So that was that expensive distance call we were trying to minimize. And for the Flickr, these are basically image-to-image comparisons. We just use Euclidean distances. Now we know that for Euclidean distances, metric spaces, there are better indexing methods because you can take advantage of the Euclidean geometry to create range trees and those kinds of things. But for a general metric space problem, you cannot apply those methods. So you're stuck with graph theory. But we use this just as an example. So anyway, the bounds were typically within 20%, which was pretty good in practice. So that was for these data sets. Then the other point I want to make here is that if I look at some of these proximity algorithms, so we took Prim's algorithm, the minimum spanning tree algorithm for Prim's, and you can see that in this table, this is for the urban Great Britain accident data set. As we looked at larger and larger parts of the graph, when we took bigger and bigger graphs, if you look at the columns which are blue, it shows you what fraction of function calls to the expensive oracle was saved by our approach. Yes, we increased local processing, but we could cut down on all the Google API calls. So you can see that on the last row, we could save 60% of the calls. So our algorithm allowed, prevented 60% of extra calls being made to the Google API, and likewise, so on. So these are all good ideas. And then, the edge landmark idea was also quite effective. And we showed that if you look at the greedy approach to creating these landmarks versus not having landmarks at all, there are considerable savings. I won't go into the details of this graph, but that's really what it shows. Okay, so with this, I'm going to wrap up my talk and conclude. So our work builds on several prior works, which shows that expensive distance oracles and metric space proximity problems can be avoided and replaced with simpler, low-cost, client-side, little graphic computations, which we want to keep it quick, but then they're not really having to go through the cloud and go and hit some big server somewhere. Okay, it's a different lens to look at very classical algorithm problems, and using a series of techniques, especially some of the approximation techniques, we could help reduce our computations to basically constant time per query, which is really what is the only thing that matters in scalable data science. We really don't want at query time things to be running linear. And you've got a large graph with millions of nodes and all that, you don't want a linear time algorithm there. You want constant time, and that's really what we achieved here. The only thing we really haven't achieved is some principled way of analyzing the approximation factors through all those methods. So those are all interesting open problems, and but in practice, it turns out that they seem to do quite well. So this is it. That's the end of my talk. I hope some of you found it interesting. If you have any questions, happy to answer them.
Question?
Yeah,
So very interesting talk. So I had a different question. So let's say I have a graph, and there could be all sorts of these questions on distances between nodes in the graph. But I first have an opportunity to make some calls to this expensive server to populate this graph with certain distances. And once the graph is sufficiently populated, then if there are new queries, I don't have to go to the server anymore. So if that is the problem, then are there some results on, for example, how many in that pre-processing stage when I'm priming the graph, how many on an average, like given a random graph, how many calls do I need to make to the server? And also given the graph, which edges should I query in order to prime things up so that then later, based on those results, I might be able to get answers for the other edges.
Right. So that, in a nutshell, is the node landmark paper. Of course, they didn't do the kind of analysis that you're expecting, the proper principled analysis, but that was their basic idea. So let me go to that slide.
But I thought the landmark is slightly different, right? The landmark is focused on certain vertices. But what I'm trying to ask is there are certain edges, right? If I know the correct information for certain edges, then based on this matrix inequality result, then I might be in a much better position to estimate the distances for the other edges.
Okay, so right, so that has not been studied. Whether asking questions on certain edges ahead of time and using that to prime the data structure so that it will help down the road has not been studied. What has been studied is asking certain questions on nodes. That's the node landmark idea. And the node landmark idea, once you believe what they've done, it actually gives you lower bounds also. Because once I have, let's say I have a single landmark, I have a single node. Okay, from that single, I pick some arbitrary node and I find all the distance to every other node. This itself is in principle a data structure that can give me upper bounds and lower bounds. So the upper bound would be if I take any missing edge, the upper bound on that length will be this triangle, right? The sum of these two edges. What is the lower bound? The lower bound will be the larger edge minus the smaller edge. You do that for all the possible, and that's how you get it. So in a sense, node landmarks is already solving the upper bound and lower bound problem. The catch is that they have to make all those early calls to prime the graph. What we are doing in the edge landmark idea is that we don't have the luxury of, let's say, getting access to that server. You are in, sub-Saharan Africa. There's no internet. You only have whatever you have with you, and you're going to work with that, right? So that's really the thing.
Thank you. Very interesting work.
Thank you.
yeah. Like all the talks, invited talks in this conference, this is also a last one, interesting talk. Thank you for the talk.
And sorry for disturbing you so much.
No, I mean,
I want to disturb you again. Okay.
I love interactions. I don't get going if people are sitting quietly. You know, so.
Okay, so what he was asking whether any study has been made on that. In fact, I was not thinking whether it could be already studied, because I was actually suggesting that if you have the whole graph in the server, can the server find out good number of landmark edges and populate to the client at the beginning of a computation? I mean, it is always publishing the K landmarks. It can be done, right? I can have a pre-processing and then finding K landmarks won't be required at the client side.
Yeah. So basically, so what you're asking is, can I design an algorithm where I've got a complete graph, and my objective is to find K edges, such that if I were to now suddenly, pretend I don't know the rest of the edges, I find your bonds through this K edges, which is some aggregate of all the low bonds is maximized, right? So that would be the problem that you're trying to solve.
I'm thinking that the server also knows that client will be in this situation and he would need the landmarks. So I give the landmarks before because I have kept them calculated. Okay.
Well, yeah, sure. I mean, the only catch is we don't really know which edges are going to be. This portion after that meta proximity algorithm, right? We're trying to create this platform which is algorithm agnostic, right? There could be a Kruskal's minimum spanning tree algorithm which only looks at a certain part of the graph, right? So, and you would have built all those landmarks for other parts. So those results are still there. You raising your hand? Okay.
Now I have a question on that final experimental table.
Which is my weak point, by the way. I have not prepared very strongly on that experiment, but
it's okay. Students have written code and you have to be responsible. That's all.
That's fine.
Okay, that's not a problem. No, it's okay. I was just suggesting, that big table where you showed in a bigger graph there is 63%. Yeah. So this is saying like how much saving is done on the expensive costs, right? But in the same row, shouldn't we have a data, just the simulation data, that how good was the estimates? Like you said, like 30%. Within 30%. I mean, that also could be calculated and reported.
Yeah, so I think this particular table is talking a little bit about how good are the bounds compared to, let's say, so for example, we are talking about the tri-scheme. The tri-scheme uses these just paths of length too, right? Whereas if you use the full graph, you get in principle the tightest bound you can get, right? So I think this is describing in a real world scenario that the tri-scheme produces bounds which are not that much off from the tightest bound you can get using edge folding over the entire graph.
So your error bounds are better, right? Tri-LB and tri-UB. Others have a...
Right. They're all different variants of our algorithms.
And this is an average over all those graphs, small to big. Is that
probably. Sorry.
Yeah. Of course. You made it. Okay. Thank you. Any more questions?
So I have a couple of questions. It's a very nice talk, beautiful. I've just a lot of questions, but I'll focus on two of them. One of them is that have you thought about the structural property of the graphs? Something like the example that you have tested, many of them seem to be planar graphs. What happens if you?
Well, I mean, I may have drawn planar graphs.
No, but the static data, they are not planar graphs.
No. Okay, so really the traffic graphs, okay, so how do you get a metric space out of a, so the traffic graph could be a planar graph, yes. But that's not a metric graph, right? Because, so how we convert a traffic graph to a metric space graph is as follows. In principle, you take any pair of nodes, so there's a traffic graph, okay? Then you create a metric space graph as follows. For every pair of nodes, you find the shortest path. You make an edge here with the full shortest pathway. If you repeat over all pairs, you get what is called a planar graph. So this is, and this, if you make n squared Google calls, you will get it, right? Assuming Google does solve this problem, it does more things, of course, but assuming it does solve this problem, that's what you'll get. So what we are saying is that this is the metric space graph we are looking at. We just don't have all the n squared edges. We will have a few of them and then
If you assume that the graph on which you're working has a structure like the planar graph,
okay.
so whatever has been given to you,
Mhm.
initial graph is a planar graph,
Okay.
then can come up with better algorithm.
Probably.
There are some of the dynamic algorithms.
Yeah, absolutely. And as you can see that this particular sort of architecture of execution, where we're trying to minimize this server calls is pretty new, even though these problems seemingly appear like 30, 40 years ago, right? So I think once these two pieces of work get traction, you will have more people following up with these kind of ideas. So maybe you should work on it.
It's a very nice problem.
Thank you.
No more questions. Let's thank the speaker again.
Thank you, Professor Das, for such an interesting session. I would request Professor Chakraborty to kindly felicitate Professor Bhupesh. Now I would request Professor Shubhashish Moyamgar to kindly come on the stage and felicitate Professor Chakraborty. Okay. So now we have arrived at the final segment of our session. We have had a day fulfilled with enriching discussions and groundbreaking research. It's been truly inspiring to see such innovation and collaboration within our community. The next session will be chaired by Professor Devanjan Sharkar. Professor Sharkar, immediately after graduation in Electronics and Telecommunication Engineering from Jadavpur University in the year 1977, joined the training school of Bhabha Atomic Research Center, Mumbai. He received the prestigious Homi Bhabha Prize for securing the first rank in the electronics discipline. He joined Variable Energy Cyclotron Center, VECC, Kolkata, a premier R&D unit of the Department of Atomic Energy, as scientific officer in the year 1979 and retired as a distinguished scientist in the year 2015. During his R&D career of 36 years in BECC, he has had significant contributions in the development of various hardware and software which are goal-oriented, import substitute, and has societal applications. He has shouldered responsible positions at WEB, including that of Head Computer and Informatics Group. At a later stage of his career at WEB, he did his PhD from Jadavpur University and became senior professor and dean academics Engineering Sciences of the Homi Bhabha National Institute, a deemed to be university. He has also served as a member of Senate of the National Institute of Technology, Patna. After retirement from the Department of Atomic Energy and before joining the Heritage Institute of Technology in 2019, Dr. Sarkar was a professor of the Department of CSE of Techno International New Town and a guest professor of the ASCE Institute of Information Technology, Kolkata. Dr. Sarkar has published more than 60 papers in different national and international journals and conferences of repute, guided a few students for their masters and PhD, and organized many national and international conferences. Now let's dive into the paper presentation, and I almost stage, but Sir has already arrived to introduce our first speaker.
Thank you, Bhagavata. Let us, in this session, we have 4 papers. The first paper is by Anitra Saha and Shoikat Roy of Heritage Institute of Technology. Shoikat Roy will present the paper. The title is A Quadrant Partitioned RRT Star Autonomous Agent. Shoikat Roy, please. You should present for 15 minutes and 5 minutes we will have for discussion.
Respected Professor Devratan Thakur, Professor Samajit Chakraborty, Professor Gautam Das, and esteemed professors, dignitaries of the dais, and my fellow students. It is a privilege to present our work, paper ID 95, entitled A Quadrant Partitioned RRT Star or QP-RRT Star Autonomous Agent. This research has been co-authored by my mentor, Professor Anitra Saha, whose guidance has been invaluable throughout this journey. Our work focuses on designing an efficient motion planning algorithm for autonomous agents operating in static environments. QP-RRT Star integrates optimality with constraint satisfaction, addressing challenges while maintaining computational efficiency. As someone new to the field, this is a special moment for me, and I deeply value the opportunity to share our findings with this esteemed audience. Your feedback and insights will be invaluable in shaping the next steps of this research. Thank you for your time and attention. Let us now begin with the presentation. In this presentation, I will briefly walk you through the structure of our work. We will start with an introduction to the problem and the motivation behind it, followed by the methodology and key features of the QP-RRT Star algorithm. Next, we will discuss the results and analysis, highlighting the algorithm's performance. Finally, we will conclude with insights, potential applications, and future directions. So, motion planning forms the backbone of autonomous systems, enabling them to navigate effectively from a starting point to a target point within an environment. It is not just about finding a path, but ensuring that the path is safe, efficient, and collision-free. Autonomous systems often operate in diverse scenarios, from cluttered warehouses to expensive outdoor spaces, making motion planning a critical challenge. Coming to challenges, first, scalability is a major hurdle. As the number of dimensions increases, the complexity of the search space grows exponentially. Secondly, while finding a feasible path is one part of the problem, achieving optimality, a path that minimizes the specific cost function, is equally important. Finally, computational complexity must be managed to enable real-time operation, particularly in high-stakes environments. To address these challenges, our work introduces QP-RRT Star, a novel approach that builds on the strengths of traditional methods while addressing their limitations. This algorithm is specifically designed for static environments, aiming to improve both efficiency and performance. So before introducing QP RRT star, let's take a step back and understand the foundation it builds upon. RRT star. RRT star is a widely used sampling based motion planning algorithm. It was introduced by Karaman and Fazoli in 2011 by their paper Sampling Based Algorithms for Optimal Motion Planning. It works by incrementally exploring the space and refining paths as more samples are drawn. The algorithm guarantees asymptotic optimality, meaning that given enough time, it can converge to the best possible path. RRT star is particularly effective in complex environments where traditional grid-based methods struggle. It incrementally improves the quality of the path as more iterations are performed, making it a powerful tool for motion planning. However, RRT star has its drawbacks. In large or intricate spaces, the computational requirements can be overwhelming. The algorithm often suffers from redundant sampling, which not only slows down the convergence, but can also lead to suboptimal solutions. Moreover, while RRT star is theoretically optimal, practical scenarios can sometimes prevent it from achieving true optimality. With this background, let's frame the problem we aim to solve. The goal is to guide an autonomous agent from a specified start state to a target goal state. The solution should minimize a cost function, for example, the length of the path or the time consumption, while ensuring that the path avoids obstacles and remains collision-free. Balancing computational efficiency with path optimality is a central challenge. In vast and complex environments, exploration can quickly become computationally expensive. Additionally, existing methods like RRT star often produce paths that are far from optimal and require significant refinement to meet the desired criteria. To overcome these challenges, our research focuses on reducing the exploration overhead while improving the efficiency of the generated paths. Specifically, we aim to address the limitations of RRT star, including redundant sampling and slow convergence. The ultimate goal is to validate our proposed QP RRT star approach through comparative analysis with traditional RRT star. Now coming to why QP RRT star. Our primary objective is to enhance the efficiency of motion planning in static environments. This involves addressing the inefficiencies inherent in RRT star, such as redundant sampling and slow convergence. The key innovation in QP RRT star is the introduction of quadrant partitioning. By dividing the search space into quadrants, the algorithm focuses exploration more effectively, reducing redundant sampling. Each quadrant guides the expansion of the search trees, improving the chances of faster and more efficient convergence to a feasible path. This approach brings several advantages. Firstly, it accelerates the convergence to a feasible solution, enabling quicker decision making. Secondly, it significantly improves computational efficiency, making it better suited for real-time applications. Lastly, by reducing redundant exploration, QP RRT star enhances scalability. We will delve deeper into these benefits in the subsequent slides. So this is an GIF animation which shows how QP RRT star expands from start node to an end node. I will come into the discussions deeper later on. So our first step is search space partitioning. The first step in QP RRT star is to partition the map into 4 quadrants. This partitioning is done relative to the start point, dividing the environment into labeled regions, Q1, which is top right, Q2, top left, Q3, bottom left, and Q4, bottom right. This structure helps localize the search and prevents the tree from expanding unnecessarily into distant areas. Once the search space is partitioned, the algorithm identifies which quadrant contains the endpoint or goal. This allows the planner to focus RRT star expansion within that specific quadrant, reducing the search space and improving the algorithm's overall efficiency. To further optimize that process, QP RRT star prioritizes sampling in regions that are underexplored. This ensures a balance between exploration of new areas and exploration of promising regions, leading to an optimized and efficient path. So, at heart of the QPRRT star algorithm is the quadrant division. We have 5 steps in the algorithm, which are quadrant division, endpoint positioning, RRT star expansion, density monitoring, and relocation of start point. So in quadrant division, the workspace is divided into 4 quadrants based on the start point, which with each quadrant labeled as Q1, Q2, Q3, or Q4. This division is not just a geometric partition, but a way to guide the algorithm's exploration, ensuring that it remains focused and efficient. This systematic approach minimizes redundant node generation and enhances computational performance. Another key component is endpoint positioning. By identifying the quadrant that contains the goal, the algorithm localizes its efforts in a targeted region. This drastically reduces the search space, leading to a fewer redundant nodes and a more computationally efficient planning process. Additionally, this focus on the goal containing quadrant improves overall quality of the path by minimizing unnecessary detours. Next, in this stage, the tree expands incrementally by connecting new sampled points to their nearest nodes. The focus here is on cost-efficient connections, ensuring that each new branch contributes to the optimality of the path. By integrating quadrant partitioning, this expansion process becomes more directed, avoiding redundant or inefficient paths and enhancing the overall convergence rate. Next, as the algorithm processes, it continually monitors the density of points within the active quadrant. If the density exceeds a predefined threshold, counter updates are triggered. This mechanism refines the sampling process, preventing over-exploration in densely populated areas and ensuring that computational resources are used effectively. Finally, QPRRT star incorporates a relocation mechanism for the start point. When the density counter reaches its threshold, the start point is shifted to the diagonally opposite quadrant. This allows the algorithm to explore previously untouched regions, expanding the search space while maintaining focus. The RRT start expansion then continues in this updated configuration, ensuring comprehensive coverage and path optimization. So in experimental validation, we have taken up some comparison metrics with which we will be comparing the results from RRT star and QPRRT star. So those metrics are path length, which is the metric measures the efficiency of the generated path. Shorter paths indicate better performance and optimality. Next is exploration efficiency. This tracks the number of nodes expanded during the pathfinding process. A lower number of expanded nodes reflects a more efficient exploration strategy. Another one is path complexity. This assesses the simplicity of the generated path, with fewer turns indicating a simpler and more practical route. Computation time. This captures the time required to generate the path. Faster computation time demonstrates the algorithm's real-time applicability. Next, coming to the comparative analysis, here is a side-by-side comparison of a path generated in World 5's environment. In the left side, we can see that the start point is here, and RRT star starts to explore in the unexplored regions randomly. So the nodes generated are all over the map. But in QPRRT star's case, it identifies the endpoint in which quadrant it is present, and then it starts exploring in that quadrant only. Another example of this is for World 6. In this case, we can see that the start point is here in this case, and the goal point is there. So going by QPRRT star, it is in Q2. So in RRT star's case, it explores the entire map. We can see that the nodes have been generated in this region, like all over the search space that was available. But in QPRRT star's case, we have explored only in the Q2 quadrant. So this is a comparative analysis of 6 words and their average average parameters that were taken. We have measured them based on the number of turns taken, the length of the path, the time taken to generate the path, and the number of nodes that was generated to ensure the path. So in RRT star's case, for world 1 to world 6, we can see that the number of nodes generated is relatively high than QP-RRT star. If we come to an average of these 6 worlds, the average number of nodes in RRT star is around 255, but in QP-RRT star it is approximately 64. I have 1 minute remaining. Okay. Okay, then I'll skip quickly. This is another comparative analysis of World 5, which goes into the detailed runs of multiple executions for the same world, starting from RRT star and QP RRT star. So performance evolution, we notice that QP RRT star achieves faster convergence compared to RRT star, making it suitable for applications. The algorithm consistently demonstrates higher path quality in static environments. Computational time is significantly reduced, enabling efficient resource utilization. And the quadrant-based approach is particularly effective in less obstructed environments, although its performance remains competitive in moderately complex scenarios. So the accompanying visual comparisons compare the paths generated by RRT star and QP RRT star, emphasizing the QP RRT star's efficiency. So one of the key limitations of this is in the scenario in which the entire quadrant is blocked. I'm sorry, I'll have to overshoot a bit. Can I continue? Yeah. Okay, so coming to the key limitation, in the scenarios where obstacles block access to the entire quadrant containing the goal, QP RRT star may not perform optimally. In such cases, traditional RRT star might provide better results. So the challenges of this algorithm is quadrant-based exploration can restrict navigation in highly obstructed environments, and the algorithm's performance is sensitive to the parameter tuning, such as density thresholds. So potential mitigations can be fine-tuning the density thresholds and exploration parameters, thus leading to optimal path generation. So another example of key limitations is for World 7, in which we can see that the start point is here and the goal point is here. So relatively comparing it, it is in Q4, but an obstacle is blocking the entire access to the quadrant Q4, thus leading to competitive results, or this is mainly the worst case scenario for the QP RRT star algorithm. So this is a comparative table for the same world, in which we can see that in some cases, for example, in this scenario, if we take number 3, the length generated for RRT star algorithm is around 341, but in QP RRT star it is 303. So in the length of the path was less, but the number of turns taken was higher. And like we can also see the significant or like competitive performance in case of the nodes generated. In average, it is approx 256, and in QP-RRT star it is 239. So coming to the concluding remarks, QP-RRT star introduces a quadrant-based partitioning to optimize the motion planning in static environments by focusing exploration within the target quadrant. The algorithm reduces computational overhead while maintaining path optimality. The strengths are, in case of path length, it reduces the path length compared to RRT star in certain cases. The exploration efficiency is better, and computation time is significantly better compared to RRT star. Yeah. So limitations we have discussed previously. And future directions can be, we can extend QPRT start for dynamic and high dimensional environments, integrating adaptive threshold mechanisms using machine learning to enhance the robustness, and investigating hybrid approaches that combine QPRT start with other pathfinding algorithms to address its limitations. These are some of the references I have used. Main was one from Laval in 1998, which introduced RRT, and then from Karaman and Frazoli, which introduced RRT star. So that is all from my side.
Okay. Yes, thank you. Any question from the audience? Any question?
Hello, thank you so much for your speech. Could you please go to like page 20? Over here, the right is your algorithm, right? The one to your right, that is your algorithm, and the path that is generated. So here the paths in and of itself, the way the path is being explored, these areas are too narrow. If the paths were wide, if they were not narrow, then it would take longer for the algorithm to get feedback on whether it's at all even going to the place where it is supposed to go, right? So if in case the paths are not narrow, they are wide paths.
So in that case, it becomes easier for the tree to directly connect with the goal point. So if we have the wide paths, we have the search spaces like in a vast case. Okay. So if we are exploring in the same quadrant, or in this case, after we can say overcoming the current obstacle, that is when it was able to overcome the blocking quadrant, when it came over through Q1, in case it had the wider paths, it would be like directly expanding the tree towards the goal point. So that will be the most optimal path, either in RRT star or in this case. So it will ultimately give you the optimal path.
Even if the goal point was quite far away.
Yes. Because it identifies the goal point in which quadrant it is, and it expands the tree in that direction only. So you will get the like most shortest path toward the goal point if there is no severe obstacles that is blocking access to that. Thank you for your question.
Any other question?
So you had mentioned that if the first approach is to divide the entire thing into quadrants, and if in one particular quadrant the density of nodes is higher, more than a threshold, then the starting point moves to the diagonally opposite quadrant. So if, for example, in one particular quadrant the density is higher than the threshold and it gets transferred to the diagonally opposite quadrant, over there also it happens the same thing. So again, if we say diagonally opposite, does it not come back to the same quadrant that it had started with?
So actually, I'll go back to this case. Yeah. So in here, this is our start point. This is our end point. Okay. So in this case, we were able to generate the path without crossing the density threshold. But in case the density threshold would have crossed, this logical start point sits in the diagonally opposite than Q1, which is in Q3. So our logical point will diagonally come over in this region, thus leading to an extended search space. The start point stays there and the tree also stays like as it is. The search space is basically widened. So thus we can explore the wider region, which can lead to the goal point. I hope I have answered your question.
Okay. Then I have a lot of questions, but that I'll ask you afterwards. Only one question I ask. Did you study your algorithm whether it works in the dynamic environment?
No, so that is a future work. We have thought of implementing the dynamic obstacle avoidance, and we will work on that. Okay. So this paper basically focuses entirely on the static environment.
Another quick question, whenever you were showing the quadrant division, no, that was not uniform, is it? For some particular purpose, this one.
Yes. So basically, we divide the quadrant based on the start point. In this case, we have the start.
So you make start point as the origin.
Yes.
Okay. Okay, then if there are no more questions, then let us thank the speaker again. Thank you.
Thank you.
Our next speaker is Sarthak Giri of Ion Group. The co-authors are Vikalpa Gautam of Sim Tech and Sneha Chaudhary of Ion Group. The title of the talk is Analyzing Social Networks of Actors in Movies and TV Shows. Sarthak will present online.
Hello, am I audible?
Yes, you are audible, but please share your presentation.
Yeah, for me, I'm seeing the pop-up post, disabled participant screen sharing. Can I get the permission to share the screen?
Okay. Can you hear us?
Yes, yes, I can hear you. Okay, I think. Uh, is my screen visible?
Just hold on.
Okay. Hello, greetings, distinguished researchers. I am Sarthak, and I am very excited to present our findings and research on social networks of actors in movies and TV shows. This paper has been conducted in collaboration with my co-authors. I and Sneha Chaudhary work together as a software engineering group. Vikalpa is a research assistant at Singapore Manufacturing Technology Institute. I'll walk you through how our research uncovers collaboration patterns and community structure that exists in the entertainment industry. These insights will offer significant value to content creators, production houses. So let's dive right in. So let's look at the motivation behind this work. The entertainment sector alone on movies and TV industry represents 400 billion market size. So this ecosystem is driven by complex. So this network analysis is important to understand the consumption pattern, to understand the behavior that exists within the network, to understand the clusters that exist and the future collaboration that might happen in the future. So let's look at the key objectives and the key research questions that we are addressing here. First is about analyzing collaboration networks, as I said previously. Second is finding out the influential actors and directors in the industry, uncovering the hidden community within the network, understanding the clusters that is not explicitly understandable, but we have understood through extensive network analysis. We try to predict future collaboration between actors and directors. So the research questions are like, who are the most connected actors in OTT cinema? How does language and regional barriers affect collaboration? Does the pattern exist between cross-cultural production? Can we even predict future collaboration? And interestingly, is how Bollywood is isolated from global cinema. Shortest distance analysis between two actors. So let's go next. So this is a subset of the network, and the right represents the zoomed version of it. Blue is the actor, red is the actress, and yellow is the movie that they've acted together in. So let's look at a few related works that have contributed to the uh, groundwork of our research. So Lander and her team performed network analysis based on centrality measures, gave the analysis of how those measures could be used in real world scenarios, but the paper lacked the practical implementation of the same. Juliana and her team did social network analysis with the fan groups, trying to understand crucial nodes by using the centrality measures like betweenness, closeness, and degree centrality in the network. But our research goes beyond that, trying to understand the collaboration patterns, clustering, and also the centrality analysis. And so Mariam and Loriza did IMDb's co-review network analysis. In there, they try to find the community detection and uncover patterns. So we also have used IMDb along with Kaggle OTT Netflix dataset. So we formed an extensive dataset combining two and tried to understand 4-5 modules, 4-5 parameters within the network. So let's look at the keyword occurrence graph that we've created. This was done by extracting the research papers from 2014 to 2022 regarding the analysis of social networks in these domains, entertainment domains. So the size of the node represents the frequency of the occurrence of the character in the document. The A's between the nodes represent that they are co-occurred together in a single document. So we see that the terms like character, story, site tend to be more frequently used in these research papers. Let's look at the research methodology behind our work. So the major part of our research was trying to pre-process, collect data, and form an extensive database from IMDb and Netflix. And we started collecting data from IMDb and Netflix. They had around more than 9,000 entries. We used NetworkX library of Python. We constructed comprehensive network where actors were nodes and collaboration formed the edges. Our analysis had 4 modules: EDA, influence and centrality module, community detection, collaboration prediction, and the picture on the right also depicts the things that were done in each of those scenarios. So I will explain each of those. The data collection, as I said, we used two classical data sets. IMDb had the gzip and gzip compressed files, name, title.principal. So we had to pre-process this data properly so that the relative fields were used, and that could help in understanding the clusters analysis that we have done. We'll present it in the upcoming slides. And the right is the Kaggle Netflix dataset. So these were the primary data sources that we have used. So let's look at the simple yet intuitive, not yet intuitive exploratory data analysis of the research that we've done. So we also try to understand the pattern of movies and TV shows from last decade. So it's quite obvious that TV shows tend to have gradual rise while the movies are decreasing. The figure on the top right shows the number of movies per cast size. So we see that 12 is the highest cast size. So generally around 1420 movies tend to have 12 cast size. So we have one cast size movie with 800 count, means could have autobiography related movies with more than 800 numbers. So these are top directors and actors in the OTT industry. Rajiv Chilaka leading in the OTT industry directorship, while in the actors in the OTT industry is Anupam Kher. So let's see crucial network insights. So I might present you these queries and you might say that these are easily available in the internet. No. So all these results that we have brought is through extensive network analysis of data. If I ask you which Chinese actors act most with Bollywood actors, so these were Chia, Hui Liu, Jackie Chan, Donnie Yen. So basically, let's look at another question. So if I ask you which Hindi actors act most with Pakistani actors, so this query generation from the
3 minutes left.
okay, so these were some of the important analysis that we generated. If I ask you what is the frequency that North Indian and South Indian movies interact, so it's 2.8%. We'll show the cluster diagram later as well. So it's just out of 100 movies that North Indian film industry produce, only 2% tend to act together with 2 out of 100 tend to act together with South Indian movies. So these were the centrality measures that we've used. Degree centrality helps in finding out the top actors who have contributed most and have unique co-starship in the network. Betweenness helps in finding out the breezes between different clusters, trying to integrate different segments of the industry. Closeness helps in finding out the nodes which are close to other part of the network which seem to have the least distance. So these were the results: actors with highest betweenness centrality, closeness centrality, and degree centrality. Collaboration prediction, we use Jagged coefficient to find out the possibility of collaboration. So Jagged coefficient is uses the idea of finding out the similar nodes based on the neighboring nodes they're interconnected to. If they have if they have large number of similar neighbors, then they are said to be similar. So the probability of connections, we see that 0.84 is highest for Joseph Garden, Gary Goldman, Marion Cotillard. Uh, so shortest path analysis, if I say how connected is Robin Williams is with Angelina Jolie. So it's just one distance. They're connected with Ethan Hawke. So the Robin Williams interacted with Dead Poets Society with Ethan Hawke, and Angelina Jolie acted together with Ethan Hawke in Taking Life. So they're just one distance apart with Ethan Hawke. So they seem to they can collaborate in the future. They're just one unit apart, and these were all the shortest paths between that could exist between two actors. If I say you what is the shortest path, sorry, I'm speeding up because the time is very slow and we have many things to present. So Jackie Chan and Rajnikant, what is the shortest distance? So they are also
1
connected by
minute
just
left.
one unit. Okay. So we did the community detection and clustering. So we formed the clusters. So we see that Hollywood is the largest cluster among those which act 90% of the time within itself. Uh, we have used Lowian clustering that received more than 90% modularity score. So modularity is the parameter that Lowian clustering uses to optimize the clustering techniques. So let's see, the frequency rate here means that the threshold of interaction between two clusters. 5% being that out of 100 movies that Hollywood generates, 5 tends to act with Hollywood horror. So higher the frequency rate means that higher co-authorship or higher interaction between clusters. So we see that at 5% frequency, Hollywood is all the clusters are isolated. Hollywood tends to interact with Hollywood horror, Hollywood TV, British. We see that some genre like Hollywood porn is isolated from Hollywood. Okay, so though they seem to be from same
Time
Hollywood
over.
industry. Okay, sorry, I'll just quickly, I'll just take one more minute. And at 2% frequency, we see that Hollywood starts pairing with Hollywood horror and all. Japanese starts interacting with Japanese porn. North Indian and South Indian movies starts interacting at 2% frequency. So even though they two are from the same country, the frequency of interaction is just 2%. But we can see that Spanish and Mexican, they are different countries altogether, but the language is same. So they are within the same cluster. So we find that the interaction is not based on the country or the boundary. It's the language that inspires the co-authorship between the actors. So we see that at 1% frequency, still the Hollywood porn is separate from Hollywood. So it's interesting that Brazilian actors can act easily with Hollywood than Hollywood porn with Hollywood, and these are also separated still. So these seem to be the most insular clusters. They tend to act within themselves most of the time. So at 1% frequency, Chinese starts interacting with South Korean, North Indian with South Indian. So let's see, at even at 0.5%. Okay.
Please
Okay.
conclude first.
Okay. Okay, so at 0.25%, we see that almost every node start interacting with each other, and Indian film industry starts interacting with other mainstream Hollywood only at 0.25% frequency rate. And among all, we see that Filipino is not connected. It seems to be the most insular cluster here that tends to act 99%, I would say, 99.75% within itself. And so these were key insights that I already summarized out of that. So yeah. So basically, our insights were about understanding the hidden patterns that existed within the networks of actors and TV shows, and this could help in understanding the future collaboration and any research insights. So basically, we could, for future scope, could be using machine learning in the collaboration prediction, because the Jagged coefficient might have estimated or generalized the network. So yeah, I'm open for any queries. Thank
Okay,
you.
let us thank the speaker.
Sorry for speeding too.
If any of you has any very quick question, only one question we can take up. Okay, since there are no questions from the audience, we thank the speaker again and we go to the next presentation by Oishi Paul.
Thank you.
This paper is by Oishik. All are from Heritage Institute of Technology. Oishik Paul, Obhisri Shaha, Arijit Mukherjee, Devjit Guho, then Priyam Das, Ankon Das, Onurina Tarokdar, and Anindo Sen. The title of the talk is Shiksha, Smart Hybrid Intelligent Knowledge System for Helping Academia. Oishik, you have 12 minutes time for presentation, and then we can have 3 minutes for discussion. Please try to maintain the time.
Good afternoon all. Myself Kaushik Pal, the presenting author of paper entitled Shiksha, Smart Hybrid Intelligent Knowledge System for Helping Academia. The contents of today's presentation are as follows. Now coming to the introduction part, the challenges faced by the teachers, students and administrators of the academia need some intelligent solution nowadays. Our Shiksha approach provides some intelligent solution in adaptable, efficient, and time efficient and adaptable, and in an adaptable framework where it integrates the solutions like here you can see the key features of Shiksha, where we automate the attendance system, coordinate-based row column mapping, behavior tracking, resource management, noise detection, syllabus tracking, safety features like fire alert system. Like in attendance, the pen and paper system is prone to errors and prone to human errors and time consuming. The biometric kiosk also create long queues in the busy hours. So our Shiksha approach automates the attendance from the CCTV data while the class is going on. The row column mapping system maps the student in the exam scenario where we have a predefined seat matrix of the students. The behavior tracking automates the tracking of student behavior of each and every individual student where we can assign marks from the behavior tracking. The resource management tracks the usage of projector, like the resources used in the classroom, like projector, tracks the projector usage for the management of that resources. The noise detection detects noises in the classroom and tracks segments the voice and noise and helps in tracking the syllabus. The fire alert system detects fires and smokes to alert in case of fire. Now, Shiksha is a 3-layer interface where the student, teacher, and administrator, that is the 3-layer of the academia, have some insights of their needs. Now, in some past works, the attendance automation was done using combination of hard cascade classifier with some CNN models. Some image enhancement techniques was also used to enhance the detection of face recognition. Some behavior detection was done using emotion recognition, where the emotion recognition was done on action unit tracking, where facial muscle movements was tracked. And some noise levels was also measured to have an idea of the impact of noise on the students. Now, our Shiksha approach is our Shiksha approach differs from these past works in some methodical ways. Here you can see the insights of the Shiksha. Now I'm coming to the detailed approaches we have used. Now, in case of attendance automation is aided with intruder detection also. We are first getting the CCTV footage, then we are detecting the faces using a custom trained object detection model. Then we have a student database where the student faces images are taken from different angles. Then we are comparing the the student faces are aligned, combined with the roll numbers of the student, and we are performing matching of the student faces with the database and the classroom detected student faces with the deep face library. Here we are having a threshold on cosine distance, where cosine distance is 1 minus cosine similarity. In the cosine similarity, the A and B are the face embeddings of the student database and the classroom detected faces. Okay, and if the threshold not passed, it is detected as an intruder. In case of behavior, we are tracking the behavior of each individual students of that classroom with their names. We have the face tracking with that behavior tracking. We have the student database, so we can track the names of the students. And in case of if the student face is not visible, we are also having the mechanism of continuing the detection of the behavior with the student name. So we can have the insights of the student behavior combined with the student names. Okay, for that we are using the intersection over union of face bounding box with behavior bounding box, so that we can track the student behavior with name. And we are using fuzzy clustering to have the mass of assigning the mass depending on the student behavior in the class. And we are having the group detection with the DB scan, where we are using the face bounding box center points as the data points, and we are detecting the student groups and combining the behavior detection with the group detection. We are having an insight of the disruptive and productive groups in the class. The row column mapping maps the students in the exam scenario, where we have a predefined seed matrix. Let us have a look on that. Here, the students sitting in the same row are having a similar y coordinate value, and students sitting in the same column are having same x coordinate value, right? So we can map the students depending on that. That is coordinate based approach. But in case of, sorry, I'm not familiar with that. Yes, yeah. The students sitting in the middle column having the same x coordinate value almost, but the students in the side columns are not having the same x coordinate value. They are varying in the long range. So here we are using the area based row column mapping, where we are averaging the area. Here, yes, here we are averaging the area of the students sitting in a single row. Like the students sitting in a single row will have the area almost equal. So we are averaging the area of that. Here you can see that the students in the first row having the same area detected with green color, then red, then blue. Then we are using the fact that the students in a column will have one student from each row. So if we traverse from in the y-axis direction for each row, then we have a single student for this column. So using that algorithm, we are detecting the columns. Okay. So using that approach, we are detecting each and every column based on the area. So okay, that is overcoming the drawback of coordinate-based system. For the projector detection system, we are not classifying. We are not having a binary classification of projector on and projector off state images. Okay. Rather than that, we are having a projector detection model, which is a custom trained object detection model. Then we are using a computer vision based mathematical approach, where we are tracking the brightness value of the brightest point. So when the projector turns on, the brightest point shifts to the projector lens, where the brightest value is almost the max, that is the 255. So here in the graph, you can see that the graph is something like that. Here the projector turned on, so the value came to 255, and then it have another spike which indicates the projector is turned off. So with that spikes, we are detecting the projector on and off state changes. Okay, rather than binary classification model. which are helping us in reducing GPU time, GPU requirement and the runtime of the project of the detection also. Now the noise detection, we are capturing the voice data of the classroom. Then we are plotting the zero crossing rate of that. We are plotting the zero crossing rate of the voice data. Here you can see that the ZCR is larger here and smaller here. It is larger in case of the voice and smaller in case of noise. We are segmenting the voice and noise part. Then we are trimming off the noise part and the silent part. Here we have the voice part only. Then we are transcribing the voice parts, which contains only the lectures and the conversation of teachers and students. Then we are having the keywords file of the syllabus. Then we are performing TF-IDF vectorization with followed by cosine similarity. We are tracking the syllabus progress with finding the matching of the keywords file with the voice transcribed text files. In the fire detection, we are having a custom trained model which detects the fire, and depending on the fire severity, the fire area is detected, and we have a alarming system of that. Coming to the results part, I am skipping those. The mean average precision value, the datasets we have used the experimental setup. Here are the results. You can see where the students are detected and the intruder is also detected. The student names are detected. The group detection result is something like that, where the student groups are detected depending on the phase, as I said, phase bounding of center points. We are having a DV scan clustering, and the behavior detection is done with the names also. Okay, the names are detected even if the student face is not visible to the CCTV camera. Okay, and we are having those behaviors segregated in the good behaviors and bad behaviors. Yes, the output of row column mapping will be something like that, where the fit matrix is from 2001 to 2009. These are the roll numbers, and the students are mapped with their faces using that fit matrix. Yes, here is the three-layer web interface of Shiksha. Yes, the three-layer web interface of Shiksha, where the student can access a chatbot for their insights. Teachers can have the students' insights, where they can see the students' behavior data, the students' attendance data, and administrator can have the access on all these data. So these are the conclusions. Shiksha automates all the key problems in the academia, where it provides insights to the three layers of the academia, that is teachers, students, and administrators. In future, we aim to improve the detection in low resolution videos with some image enhancement techniques. For more clarification in detection, we can expand the data sets, and we can also have some advanced deep learning techniques to have reduced runtime for the detections. These are the references we have used, and thank you. I'm open to questions.
Thank you, Margie. Thanks a lot and the presentation on that. Can we have one or two questions?
Thank you for working on this topic. Should help your institute also, and as this foreign professor is saying, can be sold in other engineering colleges also. But I suggest you tell your professors to have a talk with A building and whether something can be done. But I have some questions on the technical aspect. So I saw that you calculated a metric like area of intersection by area of union.
Yes, in the behavior.
In the behavior. So was that to catch cheating or finding who is whose friend or something?
No, that is used in the both ways. In the behavior tracking, we are tracking the behaviors of the student in the classroom, and we can also use it in the cheating detection. I have skipped that, but this was written in the slide. We can use that in cheating detection also. Like the behaviors are classified in 7.
But you know, I mean, even if I am sitting side by side and you have a frontal camera, the intersection may be 0, but still I can talk to someone, right? And I can cheat also. I can see sideways, but there is no. So by intersection, I mean the two pictures overlap, right?
No.
What is the interest?
Used for here we cannot see the phase bounding boxes. The intersection over union is calculated with the phase bounding box over the behavior bounding box to detect that whose behavior is corresponding to that. Here we can see that origin is reading. So here we cannot see the phase bounding boxes here. Here we can see the phase bounding boxes. So we will calculate the IOU of the phase bounding box with the behavior bounding box to have an idea of that whose behavior is corresponding to that. Like
Behavior means what? Talking in the class or
no, behavior is
looking
we are
forward?
tracking these behaviors.
Okay, this is just for okay. Speak.
We are tracking the behaviors with the students. We are not tracking the behaviors of the whole class. We are tracking behaviors of each and individual student. So
Maybe whether he is looking at his mobile or not. No, that's understood.
we are using IOU.
I was interested in where is he using IOU, means intersection over union.
Yes, we are using IOU here to detect the behavior the corresponding student, like who is reading. So we are having the reading bounding box, behavior bounding box, and then we are calculating the IOU of all the phase bounding box, whose IOU is greater. Like if the phase bounding box of origin will be something like here, okay, then it will have the IOU of reading with origin. Rather, the IOU of Oncon with reading will be 0. Like here is Oncon,
Right.
Oncon is turned around.
Okay.
So Oncon's phase bounding box will have the IOU with a value of with the turnaround. With the reading, Oncon's will be 0.
Okay, I think I will ask you in more details. I still have
Okay.
questions.
Thank you. Very interesting and good work. So some parts of it are dependent on some hardware, right? Like cameras, etc.
Yes.
So there are two questions. One is, to what extent is this currently implemented? What do you already have? Yeah, to what extent is this solution currently implemented? What do you already have implemented?
Yes, these are all implemented. These are videos taken in that civil building. We have tested on that video.
Very good. So if I want to try out some solution in my next semester's classes, so which one do you think should I try out? Which particular solution?
First, we have to make the classroom data. We need to have all the student faces taken from 5 angles. That is from the front, left, right, up, and down. Sorry, 6. That is yes. No, 5. Yes, these are 5 angles. We have to take the photos to face images. We have to have that database of the particular classroom to have the face tracking. Behavior detection is already we have the model. So for that we need that database only, then we can.
So this is implementation ready, right? So I can roll it out in my next class.
Database of that class with the roll number and the face images from 5 angles.
Very good. I'll talk to you after this. Thank you. Yes.
Any other question? Yes.
My question is the angle of the camera,
the angle of the camera from which the images are taken, your process is sensitive to that, isn't it? So for example, if a person with with any activity that you have identified, he or she does the same thing in a rotated, position.
You are talking about the behavior detection.
Behavior detection, but
The turning around part camera.
Yeah, somehow he or she is rotated, or his or her orientation is different. So will your system be robust enough to take care of that?
For have a more precise detection, we can use the libraries like MediaPipe or Delete so that we can have a measure of the angle of the face bendings. But for the images taken from the CCTV data, the image quality is that much low that these libraries will not work properly. So we have to rely on the data sets. We can expand the data sets to have that solution, but we cannot use the have the full precise result. But we can train the model on the data sets that are saying that the how much turnaround will be detected as turnaround.
Okay. Then I have one question. That is, did you think of detecting malpractice in exam hall?
Yeah, that is using phone is detected. So that can be detected. But if the student uses phone in the under the desk,
Writing on hand.
yeah, that is if he is using phone in the hand, that is detected in camera, that can be right on hand. No, we have not.
And that also can be you can think of
That can be, yeah, that behavior if he or she turns around if in a hand or something other, that is we have to track that behavior. But the behavior data set is very little available in the web, so we have to combine the web data set and our net data set to
Very nice. Thank you.
Thank you.
Talk is by Ankana Dotto on integrating AI, IoT, and drones for sustainable apple orchard monitoring in Society 5.0. All the co-authors are from Heritage Institute of Technology. The names are Ankana Dotto, Shupalpo Pal, Anidipta Pal, Shaunav Vishwas, Anil Bagh, and Diganto Sengupta. Ankana, you please try to maintain your time of 12 minutes for presentation. Ankana, please.
Good afternoon, everyone. On behalf of my co-authors, I, Ankana Dotto, am going to present our research work. Integrating AI, IoT, and drone technology for sustainable apple orchard monitoring in Society 5.0. So, agriculture plays a vital role in Indian economy, contributing approximately 20.2% in India's GDP. It also employs 50% workforce of our country. Fruit crops are an important part of Indian agriculture, and most commonly consumed fruits of India are banana, apples, and grapes. So, improvement in farming techniques of these fruits is beneficial for not only economic but also a sustainable growth. But fruit crops did not receive as much light, receive the light of research as much as the other crops did. And among fruits, there are less research works on apples than banana or grapes. Now, as we all know, Society 5.0 stresses on mainly 4 factors: AI, IoT, big data analytics, and robotics in various fields for creating a human-centric, sustainable, and inclusive socio-economic system. So, working upon precision farming will help us get one step closer towards achieving Society 5.0. Hence, we propose SAMS, Smart Apple Orchard Monitoring System, an AI-IoT enabled framework that is capable of processing multimodal data for apple orchard monitoring. But during our research work, we faced multiple challenges. Firstly, as we are working on this project from West Bengal, collecting on-field accurate data was difficult for us. Also, for the same reason, testing our system was also difficult. There are already many research works done on similar problems, so one of our main concerns was to increase the accuracy of our system to add some progress to the existing works. As we all know, apples grow mostly in colder regions, especially in India, especially in mountain regions. So keeping in mind that network strength is not always good in farms or fields, especially in mountain regions, creating a system that can tackle this problem took us some effort. And last but not the least, we aim to make our system as accurate and precise as much as possible. So distinguishing one apple from another was another challenge faced by us. We solved almost all the problems above discussed here, and we will discuss the solution during the course of this presentation. Now, the existing literature works showcase the use of AI, IoT, and drone technology for smart farming and intelligent apple orchard monitoring, but none of them showcase the use of multimodal data processing for yield prediction or health monitoring. So, our study also takes into consideration 3 further soil components that are nitrogen, phosphorus, and potassium. Our study shows 98.19% accuracy in apple counting, 53.66% accuracy in apple classification, and 96% accuracy in leaf health classification. So now I will quickly take you all through the working of our system. Our system architecture mainly consists of 3 parts. The IoT sensors, the ML models, the IoT sensors, the ML models, and the multimodal data processing for yield prediction. At first, the ESP32 camera mounted on drone captures images of apple orchard at an interval of 2 seconds and uploads them to cloud. It has also a memory card that acts as a fail-safe mechanism when the network connection is disrupted. For that time period, it stores the images in it, and as soon as the network connection is restored, it uploads the images to cloud. It also erases the images from the storage to clear up local storage. Then comes the IoT sensors. We have integrated a soil pH sensor, a soil moisture sensor, an NPK sensor, and DHT11 as humidity sensor. All these sensors measure the parameters like soil moisture, soil pH, nitrogen, phosphorus, potassium level in soil, and ambient humidity and temperature respectively. All these data are uploaded to cloud in CSV format. From here, ML takes over. we have the images are segmented and stored as two separate arrays. One array of images contain the annotated images of apples, and another array contains the residue of the images, which are the apple leaf images. Now we have trained a yellow VTX model for this segmentation task. Then we have trained the ResNet 152 classifier for detecting if the apples are diseased or not, and another ResNet 152 classifier that for detecting the diseased leaves. Finally, the yield is predicted by a combined analysis of soil parameters and the overall health of the tree. The apple and leaf health tells us the overall health of the tree, and the soil parameters are for added validation. That says if the environment is ideal for maximum yield. This is a simplified diagram of our working of our system. So for results, we have validated our system on publicly available unlabeled image data sets, and for sensors, we have validated them in a simulated environment where they gave satisfactory results, as you can see in the slide. So this assures us that once set up in real environment, they will generate reliable real-time data. For the ML part, you can see the performance matrix of YOLO VTX model. Before choosing ResNet 152 classifier, we gone through a comparative analysis between voting classifier and ResNet 152. The voting classifier is command of random forest, logistic regression, SVM classifier, decision tree, cat boost, and LGPM. I have also given the Animax model performance matrix. This Animax model, I forgot to mention actually. This Animax model is used for our multimodal data processing. So overall, this is a transformative approach for smart apple orchard monitoring. It classifies apples and leaves as per their diseases and counts and predicts yields based on soil parameters. We can implement a more effective filtering mechanism for sorting good and bad apples by placing a camera on conveyor belt in apple segregation area and deploying a model for detection of bad apples. We can sort the bad apples and eliminate them easily. These are the references which we use for our work. So, as I have discussed our work with you, now I am open to any kind of queries. Thank you.
Just thank the speaker. And if you have any question, please feel free to ask.
Which data set you have used for training?
We have made a combined data set by using publicly available data set mostly on Tableau and RoboFlow.
Oh, they were labeled.
Yes.
Okay. Have you done any comparative analysis of your result with the earlier works that you have shown in the literature review that there are?
Yes, we have, and we have given that table in our paper.
Okay. Okay. Yeah.
Is it something like that when you are taking the snap from the mountain region, apple orchard? So there is sometimes the microclimate situations create some hindrance to take the snaps. Usually, sometimes you'll find you are just flying over the low region, but due to the cloud or fogs, it's not possible. So that kind of image processing, are you implementing in that?
We have thought about it, but we didn't had enough data set for implementing that as of now.
Any other question? This is the last session, last technical session of this ICA 2025. So you can ask some questions now. Okay. So if there are no questions from the audience, let me ask one question. This work is only for monitoring or taking any corrective action also? Because I did not find any point in seeing what is the NPK values and all. This, if I find that this apple growth is not good, then I may change the concentration of NPK, etc.
Yes, yes.
Are you doing that, or are you thinking
No, I'm
in that
giving-
line?
Yes, I'm only giving the data of the health of the tree, like of the field of the tree, everything, and the corrective action has to be taken by the orchard owner or someone farmer. So we are only giving the analysis.
But this data is to be taken at a periodic interval, no?
Yes.
Maybe every 3 days or every week, something like
Yes,
that.
yes.
So that how the apple growth is going on, or it is deteriorating, etc.
Yes. The sensors will be, installed at the field all the time. It will be a system installed at the field permanently.
Okay. So thank you. Let us thank the speaker once again. It was a nice talk.
Thank you. Now I request Professor Anup Kumar Sen to kindly come on the dais and felicitate Professor Devranjan Sarkar. Conference and applied algorithms. It is my great privilege to welcome you to this valedictory session. Over the past 3 days, we have witnessed an extraordinary confluence of ideas, innovations, and insights. This conference has been a vibrant platform for researchers, practitioners, and thought leaders to exchange knowledge and explore the frontiers of applied algorithms. Before we start the valedictory session, we will take a 5 minutes break to set the stage. Okay. During these 5 minutes, all the participants, presenters, and the attendees, you have received a feedback link in your email or WhatsApp. I would request you all to kindly provide the feedback for the conference during these 5 minutes. Thank you.
Student in India, right? Each student is there. So what happens in the by the time he's staying at the right.
সেন্টার করে রেখে দিয়ে বাদ বাকি গুলো অ্যাডজাস্ট করে সফটওয়্যার যারা শান্তি পাবেন আমি যে ইনোভেশন করি
Session has been a testament to the transformative power of algorithms in addressing real-world challenges and advancing industry standards, particularly as we navigate the shift towards Industry 5.0. It is my pleasure to acknowledge and celebrate the efforts of our paper presenters. Your hard work, dedication, and innovative research have significantly enriched this conference. To honor your contributions, we will now proceed with the presentation of certificates. I would request our CEO, sir, to kindly come on the dais. Next, I request our principal, sir, to kindly come on the dais. Sir, ask me, please. Okay. Next, I will request our program chair, Prosenjit, to kindly come on the dais. Next, our general chair, Professor Subhash Mundar, kindly come on the dais. I would also like to call on the stage our registrar, sir, kindly come on the dais. So now we will be starting with our certificate. I would like to call our CEO, sir, to kindly hand over the certificate to Devaditya Ghosh, which is to be collected by Shalini Pramanik. Next, I would like to call on Aniditya Pal from Heritage Institute of Technology, Kolkata. I would like to call Oishik Pal from Heritage Institute of Technology, Kolkata. Next, I would like to call on our principal, sir, Professor Babsudeb Choudhury, to kindly hand over the certificate to Ankona Dotto from Heritage Institute of Technology, Kolkata. Next, I would like to call on Professor Reshma Roy Choudhury from Heritage Institute of Technology, Kolkata. I would like to call Nilanjana Basu, Professor Nilanjana Basu. Professor Nilanjana G. Basu. Next, I would like to call our registrar, sir, to kindly hand over the certificate to Professor Dilina Bera from Heritage Institute of Technology, Kolkata. Sir, I would like to call our student Shoikat Roy from Heritage Institute of Technology, Kolkata. Next, I would like to call the program chair, sir, to kindly come on the stage and hand over the certificate of attendance to Professor Anil Kumar Bag, Heritage Institute of Technology, Kolkata. Next, I would like to call Somjit Datto, Professor Somjit Datto from Heritage Institute of Technology, Kolkata. Next, I would like to call upon the general chair of the event, Professor Subhashish Majumdar, to kindly come on the stage and hand over the certificate to Professor Ritpurna Sinha from Heritage Institute of Technology, Kolkata. Next, I will request our CEO, sir, to kindly address the gathering.
Thank you. So, distinguished on the dais, off the dais, dear faculty members, all the participants, our students, I think it was a great deal. We had a very good, nice conference as I got the feedback. Last 3 days was really hectic and a lot of papers were presented and we also felicitated those who have done really well. But other than those who have not done really well, their projects were also quite good, and it may be considered if they do little more effort in due course of time. And the last dinner, I am sorry I could not join, but I hope that it went quite well. And you should note that our proceedings will be in the Elsevier magazine, and which is a great deal. It is not all the proceedings are in such a reputed journal. So I hope you have all enjoyed. So thank you very much. And we wish that next conference will be in 2026 again. Thank you.
Thank you, sir, for the motivating words. Finally, I request one of the organizers of the conference, Professor Dinobandhu Bhandari, to kindly come on the stage and deliver the vote of thanks.
Everyone, as we draw this remarkable conference to a close, it is my privilege to deliver the vote of thanks on behalf of the organizing committee. The success of the International Conference on Applied Algorithms has been made possible through the collective efforts of many individuals and organizations, and it is with great gratitude that I acknowledge their contributions. First and foremost, I extend my heartfelt thanks to our advisors, Sri H.K. Chaudhary, Sri P.R. Agrawala, Sri P.K. Agarwal, Professor Basud Chaudhary, Principal, Professor Sujit K. Borua, Registrar, for their unwavering support and guidance throughout this journey. A special thanks to our steering committee chairs, Professor Bhargav B. Bhattacharya and Professor Sandeep Sen, for their invaluable leadership and direction. I would also like to express my deep appreciation to our general chairs, Professor Amitabh Bagchi and Professor Subhashish Majumdar, program chairs, Professor Subhashi Nandi, Rajat K. De, and Professor Prosenjit Gupta, and my fellow organizing chairs, Professor Subhajit Dotto and Professor Sujoy Saha. Your dedication and meticulous planning have been instrumental in making this event a grand success. A big thank you to Sri Manoj Salaogi, our finance chair, for his diligent management of financial matters, and to our publicity chairs, Professor Diganto Sengupta and Professor Nilanjana G. Basu, together with all my colleagues and our student, Mohit Jena, for ensuring widespread visibility and engagement. To the members of the Technical Program Committee, including our esteemed reviewers, along with the organizing committee, your hard work behind the success has not gone unnoticed. Your commitment to excellence has ensured the smooth execution of every aspect of this conference. We are privileged to have distinguished invited speakers, including Professor Gautam Das and Professor Samarthi Chakraborty, who shared their invaluable insights and expertise. Our gratitude also goes to our chief guest, Professor Sanjay Paul, and guest of honor, Professor Souvik Bhattacharya, for their inspiring presence and words of wisdom. A special mention to our session chairs, Professor Subhashi Nandi, Professor Susmita Sudkole, Professor Partha Bhaumik, Professor Rajat K. De, Professor Sujoy Saha, Professor Navendu Chaki, Sanjay Saha, sorry, Professor Amitabh Bagchi, Professor Anup K. Sen, Professor Partha Basu Chaudhary, Professor Anshuman Banerjee, Professor Prosenjit Gupta, Professor Saurabh Chakraborty, and Professor Devranjan Sarkar for their excellent moderation and guidance during the sessions. We had the privilege of listening to 30 outstanding papers, presentations, each contributing to the depth and breadth of this conference. Your research and presentations have been a cornerstone of this event. I would also like to extend my thanks to all the authors from all over the world for considering our conference for their invaluable submissions. I'd like to extend my sincere appreciation to Joint Registrar Arvind Srivastava and Campus Administrator Lieutenant Colonel Amitabh Gosdostidar for their crucial contributions in ensuring the smooth functioning and logistics of this event. A special thank to Mr. Devashish Karmukar and his team from Systems for their exceptional support in managing both the online and offline sessions seamlessly. Your efforts have been vital to the success of this hybrid conference format. Additionally, I would like to express my gratitude to the Department of Media Science, the Heritage Academy, for their outstanding contributions. Your effort in media coordination and coverage have greatly enhanced the outreach and documentation of this event. A heartfelt thanks throughout the conference for ensuring everyone was well fed. A heartfelt thanks to Prabhat and team of Canteen for ensuring that everyone was well fed and refreshed throughout the conference. Your contribution has been greatly appreciated by all. A special mention to Pradeep, sitting there or standing there the whole day, for whole 3 days, for his impeccable management of audio, visual and lighting systems in the SBA auditorium. I would like to convey my heartfelt thanks to all contributors, the cultural program for their mesmerizing performance that aptly reflected the cultural aspects of the City of Joy, not only the conference. I would also like to thank all our anchors for comparing 13 sessions in the 3-day-long event. Being a computer science professional, we understand the difference between greater than and greater than equal to. They are always with us, our CEO, Pradeep Ji, Subhashish Majumdar, Subhashish and Prosenjit and Diganto for their suggestions in addressing many intricate issues. Thanks to you, sir. Lastly, my heartfelt thanks to all the participants, delegates and attendees. Your enthusiasm and active engagement have been the lifeline of this conference. We are excited to announce that the proceedings of this conference will be published in the esteemed Springer Verlag LNCS series, which will further disseminate the valuable knowledge shared here. If I have inadvertently missed anyone, please forgive me. The contributions of each and every one of you have been instrumental in the success of this conference. I thank you all once again for making this conference a resounding success. Thank you. I'll just end it.
Let us thank Professor Gandhi with a big. He really deserves it. Without him, it would have been possible, and without him, I won't have ventured.
Actually, Professor Bhandari is a very clever man. He wanted standing ovation.
And now we'll gather for the group photo. I would request Professor Gautam Das and Professor Shomadip Chakravarti to kindly come on the stage. Also, along with them, I would request all the persons who have received certificates kindly come on the stage. I would request every one of you to kindly come on the stage. I would like to call on stage Chandrasekhar Kumar. I would like to call on stage all the student volunteers also for their extremely appreciable work throughout the conference. Yes.
দাঁড়িয়ে না আসলে ভালো লাগে
দুটো চেয়ারের উপর পা দিয়ে মাঝখানে দাঁড়া সঞ্জয় जल्दी करो लेट मत करो ছবিটা হয়ে যাক
রেডি तो एक ऐसा एक फोटो दे
Thank you. ছবি করতে সঞ্জয় করলে সেটা বাদ দিতে আজকে আপনার বন্ধ থাকে এটা কেটে দাও